So today we're going to start a new unit on rational functions and rational exponents. So we're actually going to start off by looking at rational exponent first. So ignore the fact this is 2.4. Normally I cover rational functions first, but we sort of changed the order around a little bit and cover rational exponents. But before we do that, let's just have a little bit of review of the exponent laws, exponent rules, as we've learned them from grades 9 and 10. So before you continue on with the video, if you haven't done the warm-up, it would be really good if you attempted to warm up yourself and see if you could actually get the answers that I'm about to get. So the first one, we have x to the 4 times x to the 7. So this is the product rule. So here we have the same base and we're multiplying two powers of the same base. So we're going to have to add the exponents. So this is going to be the same thing as x times 4 plus 7, which is x to the power of 11. So a general rule here is that if we have x to the power of a times x to the power of b, in other words, our base is the same, then we just add the exponents together, and that's how we simplify it. Our next question is we have x to the power of 9 divided by x to the power of 3. So here's the quotient rule, where now we're dividing one power by another power. Again, the base always has to be the same. So in this case, we're going to subtract the exponent. So x to the power of 9 minus 3, which is x to the power of 6. So in general, if we have x to the power of a over x to the power of b, then this is just going to be x to the power of a minus b. Our third example over here is we have a power to the power. So if this is x to the power of 3 all to the power of 4, so really we want to expand this. This is really x to the power of 3 times x to the power of 3, x to the power of 3 times x to the power of 3. So basically that's what the power means. So the 4, we have 4 of those things multiplied together. Well, we just take our product rule, and basically this is going to be the same thing as x times x to the power of 3 plus 3 plus 3 plus 3, which is x to the power of 4 times 3. So this, hopefully we can see why the power law exists, or why that works the way it does. So this is going to be x to the power of 12. So in general, if we have x to the power of a all to the power of b, this is the same thing as simplified to x to the power of a times b as the exponent. So here are some more examples that are a little bit more difficult in terms of simplifying. So here there's a mixture of powers and product rules and quotient rules, and so really the order here doesn't matter in terms of there might be several ways to solve this. Just choose the one that makes the most sense to you and that follows the exponent laws. So the first things I like to do is here we have 2 powers to a power, so I would just like to take care of that first. So this would be so again, the power to a power is to take the exponents and multiply to the outside exponent. So really remember when there's no exponent, or on the coefficients here of 4, there's really exponent 1. So this is 4 to the power of 3 times a to the power of 3 times 3, which is a to the power of 9, and then b to the power of 5 times 3, which is b to the power of 15. So I just leave that in the first bracket, just show that I sort of simplify that first set of brackets, and then I'm going to do likewise for the second one. So in this case, it's going to be 1/2 squared, which is going to be 1 over 4. So I'll just do that in my head. A squared is going to be a to the power of 4, and b to the power of 2, b to the power of 1 raised to the power of 2 is going to be b squared. And then on the denominator, because I don't have a power to a power there, I'm just going to recopy that down again. So a to the power of 16 times b to the power of 8. Then the next step I might take is maybe just expanding, or sort of simplifying the numerator. So I have various powers, product rules or product situations. So let's do 4 to the power 3 first. That's going to be 16 times 4, which is 64. So 64, I'm going to multiply by a quarter. It's going to be 64 over 4. A to the power of 9 times a to the power of 4, which is going to be a to the power of 13. And then b to the power of 15 times b squared, which is going to be b to the power of 17. And in my denominator, I have, again, just going to copy down 4, a to the 17, b to the power of 8. Another step we're going to take is just simplify 16 over 4, which is 16. I'm going to take one further step just to make it a little bit faster. Divide by 4 again. And so it's going to be 4. Have 8 to the power of 13. Divide by 8 to the power of 7. So we could apply the exponent law, the quotient law, go 13 minus 7. We're going to get a negative 4 up top. How I like just to do this is sort of one quick step, is recognizing that if we want to think about it, there's 13 a's multiplied together in the numerator, 17 a's multiplied together on the denominator. So when we do all the canceling, we're going to get left with 4 as a numerator in the denominator. So I'm going to get a to the power of 4 down here. So that all cancels out. And same thing, b to the power of 17, divided by b to the power of 8. You can think of it as I'm going to get 17 minus 8, which is 9 b's left on top. So I get 4b to the power of 9 over 8 to the power of 4. So that's that question in terms of simplifying that power. So the next one is basically pretty much the same thing, except now we have some negative exponents and what we need to sort of do with that. So I'm just going to take the same strategies I did before, and I'm just going to do the power to the power first. So here I'm going to get 2 to the power of negative 3, x to the power of negative 3, y negative 2 to the power of negative 3 is going to be y to the power of 6, and then get z to the power of negative 3. And then the other one, power to the power, and get x to the power of negative 8, y squared, z to the power of 6. And in the denominator, not much is happening there. We're just going to get left with 8xy to the power of 5z squared. Now we're going to sort of simplify the numerator again, and I just apply various product rules with the variables. So I'm going to still 2 to the negative 3. So x to the power of negative 3 times x to the power of negative 8 is going to leave me x to the power of negative 11 because I'm adding the exponents together. So negative 3 plus negative 8 is negative 11. Y to the power of 6 times y squared, that's going to be y to 6 plus 2, which is 8. And then z to the power of negative 3 times z to the power of 6, that's going to leave me with z to the power of 3. And then in my denominator, I'm still going to leave everything as the same, x y to the power of 5 z squared. I'm going to take each variable and go off. You know what, I'm just going to go off and sort of this 2 to the power of negative 3 is sitting there. So again, what this negative exponent means, it means that we flip our base or reciprocate our base. So in this case, 2 is really the fraction 2 over 1. So we're going to reciprocate the base. So it's going to be 1 over 2 to the power of 3. In this case, we're going to see that this is 1/8. So 1/8 divided by 1/8, we're going to get 64 in my numerator. So my denominator, so I'm just write that there. And now I'm going to start taking care of my variables. So I get x to the power of negative 11 and x divided by x. So here we can think of it as negative 11 minus 1 is going to be negative 12. Or really, I could do the other way, and you can think of reciprocating. It's not the best way to describe it, but if it's a negative exponent, we're really bringing that base to the other part of the fraction. So if it's in the numerator, we sort of bring that back down to the denominator, and then the exponent becomes positive. And likewise, if it was negative in the denominator, we could bring that up to the numerator and make the exponent negative. Sorry, make the exponent positive. So that's really the idea of reciprocation. That's the net effect of it when we reciprocate. So here I'm going to get x to the power of 12 in the denominator. y to the power of 8 divided by y to the power of 5. So y is going to be in the numerator, so y to the power of 3. And then I got z cubed divided by z squared, so it's going to leave me z on top. So it's a little bit crammed in there. Let me just kind of move that down a little bit and rewrite the exponent so it's a little bit more clear. So that's going to be y to the power of 3. Okay, so that's the warm-up and going through. So it's really important that we sort of understand and remember the exponent laws as we know them, and because we're going to sort of take advantage of that, and we'll go to rational exponents. So one last warm-up we're going to do is this question over here. So just dealing again with negative exponents, and here we want to evaluate. So again, the idea of negative exponent is that we reciprocate our base or flip our base, and the exponent becomes positive. So in this case, 3 to the power of negative 2 is really 1 over 3 squared, plus 3 all over 9 to the power of negative 1 is going to be 1 over 9. And then 3 to the power of negative 1 is going to be 1 over 3. So now we're just going to do some fraction arithmetic. So 1 over 3 squared is going to be 1/9. So I'm going to convert 3 into a common denominator of 9. So it's going to be 27 over 9 divided by 1/9 minus 1/3. So I'm going to convert that to be 3 over 9. So in this case, I'm going to get 28 over 9 divided by, well, 1 minus 3 is a negative 2 over 9. Continue up there. So 28 over 9. So instead of dividing by a fraction, we'll multiply by the reciprocal. So that's going to be multiplied by negative 9 over 2. So in this case, we're going to get some reduction. The 9's cancel out. 28 cancels with the 2. And we're left with 14. So it's going to be just the answer of negative 14. So that's our final answer there when we evaluate that. Notice that didn't need a calculator. We could plug that into the calculator and get non-exact answers. In this case, because we're just applying the exponent laws, we will, and working with the fractions directly, we will get an exact answer. So after today's or this lesson, we'll be able to understand the meaning of rational exponents. We're able to solve or simplify expressions involving rational exponents. So I gave a hint here. Rational is really a fancy word to say things are a fraction. So in this case, when we talk about rational exponents, that means exponents are fractions. And what exactly does that mean? So in grade 9, we learned the fundamental exponent laws of the product, quotient, and power laws. And then we also learned that anything to the power of 0 is equal to 1. And then in grade 10, we learned what a negative exponent means. And so the net effect was that, again, we flip our base or reciprocate our base and the exponent becomes positive. And finally, this year, we'll talk about rational exponents. In other words, when an exponent is a fraction, what does that mean? And how can I go off and evaluate and simplify things? And the key thing that we're going to discover is that really a radical is another way to express a rational exponent or exponent that's a fraction. So we'll be able to translate terms expressed as a rational exponent to a radical and vice versa. So we're going to go back and forth in either way, really understanding that there's just two different ways to write things in math, two different notation to mean the same thing. So I'm going to start off with an example we're just going to explore. 8 to the power of 1/3. What exactly does that mean? How do we even get it? Well, we can't even get an answer if we don't actually understand what that might mean. So the one thing that I would like to do is go off and explore wherever that value is. Don't know what it is, but what happens if I take 8 to the power of 1/3 times 8 to the power of 1/3 times 8 to the power of 1/3? Well, the product law tells me that we add up the exponents. This is really 8 to the power of 1/3 plus 1/3 plus 1/3. So this is going to be 8 to the power of 1. So in other words, 8 to the power of 1/3 times the power of 1/3 times 8 to the power third times 8 to the power third, when we multiply them together, we're going to get 8. So that sort of gives us a hint to what 8 to the power 1/3 means. In other words, just one of these. Because each one of these has the same value. We don't know what that answer is, but they have the same value. But we're going to multiply it by itself 3 times, and we're going to get the answer 8. So it really comes down to, fundamentally, we think about it, that if we say 8 to the power 1/3 is equal to x, whatever that is, we don't know what x is, but if we take x times x times x, that's going to equal to 8. So we could almost kind of see that really x is what number multiplied by itself, in this case 3 times, equals 8. So we know that in this case it's going to be 2 times 2 times 2, that's going to equal 8. So that's what we discovered, that 8 to the power 1/3, that's equal to 2. Well, let's go off and look at another example and really applying the same strategy or the same technique that we just did in solving that, or really understanding what that rational exponent might mean. So in this case, we have 32 to the power of 5. So again, we might say let x equal to 32 to the power of 5th. We don't know what that value is, but again, we're going to take x times x times x times x times x, and we know that this is going to be 32 to the power of 5th to the power of 5, because we multiply by itself 5 times. So really, this is going to equal to 32. So what number multiplied by itself, in this case, 5 times, is going to equal to 32? Well, a little mental math tells me that, well, it's actually 2 again. So 2 times 2 is 4, times 2 is 8, times 2 is 16, and times 2 one last time is 32. So we recognize that 32 to the power of 5th is also equal to 2. So what can we say about this in general? So we're saying that really if we have x to the power of 1 over b, this implies that, well, what number multiply by itself b times? So here, how can I express this? What number multiplies by itself b times? So we have x, well, I don't want to use x again, but really what number multiplies by itself b times is going to give me the answer x. So the way we could actually write this is with a radical, where x is my radicand and b is my radix. Okay, so this is really another way of expressing the same thing, except that we're just using the radical symbol instead of a rational exponent. So we should be able to go back and forth between these two, even though it's just a different notation with the same meaning. So our next example is a little bit different. We have 64 to the power 2/3. Well, again, the idea of a rational exponent, or exponent as a fraction, throws us off a little bit. We have an idea what's happening with when the denominator, because that's what we recognize that in here, when we have a denominator of b, we're going to have to multiply that number, whatever the answer is, b times by itself to get x. So we could actually break up this exponent to be 64 to the power of 1/3 all to the power of 2. Because if we take the power to the power law, we have 64 to the power of 1/3 to the power of 2. We multiply those two exponents and we get 6 to the power of 2/3. So we really separated the numerator and denominator of a rational exponent. Well, we know that this means this is really the cube root of 64. So this is what we call cube root. And here, what number multiplied by itself 3 times gives us the answer 64. And then afterwards, we're just going to square it. So in this case, it's going to be 4 squared, which is 16. Okay? So this is now a more general thing where we have any number raised to the power of a rational exponent. So let's say this is a over b. So that's the exponent, a over b. We're going to say that this is really the same thing as the bth root. So that's how you sort of say the radical. How do you sort of pronounce that? So if it's 4, you would say it's the 4th root. If b was 7, we'll say the 7th root. In this case, if b was 3, we have a special word for that for a cube, so it's a cube root. So it's the bth root of x, and we're going to take that all to the power of a. Okay. Recognize that this is always also the same thing as x to the power of a, and we take the bth root of that. So both of those mean the same thing, although when it comes down to calculation, it's much easier to do this. In other words, take the bth root of x because it's going to be a much smaller number, then raise it to the power of a, as opposed to taking x, raising it to the power of a first. Now we might get a very big number, and then it might be very difficult to calculate the bth root of that. So let's go through some explicit examples. We're going to rewrite the following as a power with positive exponents. So that's one thing in this unit that's going to come up over and over again. We either want an answer as a simplified radical, or we want it with exponents, but all the exponents need to be positive. It could be a fraction. In fact, we can avoid it, but we always want exponents to be positive. So the cube root of 36, this is really the same thing as 36. So remember, a denominator is going to be 3. And we could kind of see that, well, there's an implied exponent 1 on the 36. So this is going to be 36 to the power of 1/3. Okay, likewise on this example, so 4, the radicand, is going to be my base, 4. And then my rational exponent is going to come from 3. It's going to be my numerator. And the radix of my radicand is always going to be the numerator, so the denominator. So it's going to be 4 to the power 3 over 6. And just like if it was 3/6 is a fraction, even though this is an exponent, we always want to simplify that. So this is 4 to the power of a half. Okay, one other example here. We got the 9th root of 4 to the power of 5. So again, the radicand is my base, so it's going to be 4. The exponent is going to be my numerator, in this case is 5, and my radix is going to be my denominator of my rational exponent, so that's going to be 9. So this is 4 to the power of 5/9. Okay, so just going through this is really kind of the same thing here. I can get 7 to the power of 5 over 4. And this one's a bit tricky because we have a -3 inside brackets, so we need to keep that inside my base. And here is going to be 6 over 3, which is, simplify the exponent, which is going to be -3 squared. Okay, so we're not going to evaluate that. We're not asked to evaluate, but just to rewrite as a power of positive exponents. So in this example, we're going to go the other way, where we want to rewrite the following rational exponents into radical form. So we go back to the opposite. So the base becomes my radicand. So here it's going to be 5. My denominator, so I'm going to work with the denominator first. That's going to be my radix. So that's 2. And then we're going to take this all to the power of 7. So I'll put the exponent on the 5 here, on the 5. I go on the outside as well. So one thing to note is that we never write the radix of 2. This is an applied square root. So whenever the radix isn't written, it's applied to be 2, which is something that we've been working with all along. In other words, it's just a square root. So this is going to be just a square root of 5 to the power of 7. Okay, so I'm not sure there's an example here, but one thing that we're going to note is that square root of x, what's that as a rational exponent? Well, again, there's an applied radix of 2 here. So that's the denominator of my exponent. And since there's an implicit 1 for the power for the exponent on x, really that's going to be x to the power of 1/2. So that's one thing that we really have to come to know and remember, or kind of see often, is the square root of x really has the exponent 1 over 2. So here we have an example of -4 to the power of 8 to the power of 8 over 5. So again, our base is going to be negative 4. That's going to be to the power of 8. And then we want the fifth root of that. So again, the denominator is my radix. The numerator is the power. So again, we could write these a different way. So this one's going to be a little bit tricky because we have a negative there. So really it's a negative exponent. Let's deal with that first. So negative exponent means that we reciprocate our base. So this is 1 over 9 to the power of 5 over 3. So we don't want to sort of carry that negative exponent to my radical. Let's deal with the negative exponent to make it positive. And so now my radicand is going to be 1 over 9. And here it's going to be the cube root because that's my denominator. And in this case, I'll write the exponent on the outside. Again, either answers are correct, so that's 1. Or if you want to keep the exponent on the inside, the radical sign, it'll look something like 1 over 9 to the power of 5, and we want the cube root of that. Okay, really, it's something like this. When we have a fraction, especially 1 is the numerator, we might want to simplify that a little bit further and say that this is the cube root of 1 over 9 to the power of 5. Okay, so a little bit tricky. That's not the best form I wrote here. It almost looks like 95. We need to take care of our work. So I'll write this a little bit bigger, 9, and there's the little exponent 5. So just working through these, the other examples, now we want to evaluate. So on this part, now you really want to go and use a calculator, because one of the things that you might need is to take a sixth root. So for example, the sixth root here is 64. So your calculator may or may not accept a fraction for the exponent. Some calculators do these days, but almost every calculator does have like the nth root button. So here we're going to convert this to a radical. So this is really the sixth root of 64. So depending on your calculator, you might have a symbol that looks like this, where you press that and you sort of have to fill in the radix. You give it the radix. Or, hopefully now we can understand what's going on here a little bit. The button on your calculator might look something like this, x to the power of 1 over n. So really seeing that this is implying the same thing. In this case, you have to fill in the n for the radix for your radical. So in this case, hopefully you can try this on your calculator. The sixth root of 64 is going to be 2. The fourth root of 16, this is also 2. 2 times 2 is 4, times 2 is 8, times 2 is 16. So this one, we are just dealing with a negative exponent. It's not even a rational exponent, but we'll just do it anyway. So we want to reciprocate our base. That's going to be 5 over 6. The exponent becomes positive, which is going to be squared. So this is going to be 25 over 36. So this question D is sort of an extension on A. So we discover that, well, this is going to be really the sixth root of 64. And again, it's easier we do the exponent on the outside, because 64 to the power of 5 is a pretty big number. And in my head, there's no way I could actually do the sixth root of that big number. In this case, it's easy for me to do the sixth root of 64, which I did above, which is 2. To the power of 5, and 2 to the power of 5 is 32. All right. So here's an example of the negative exponent. So we're just going to take care of the negative exponent. We're going to reciprocate our base. That's going to be 1 over 8, all to the power of 5 over 3. So this is the same thing as the cube root of 1 over 8 to the power of 5. So the cube root of 1 over 8 is really the same thing as 1 over the cube root of 8 to the power of 5. Well, the cube root of 8 is 2, so it's going to be 1 over 2 to the power of 5, which is 1 over 32. All right? So once we get to the fractions, it is a little bit tricky. So question F, got to be careful because now the negative is not an exponent, it's just in their base. So here we want the fifth root of negative 32 squared. Now, if this was the square root of negative 32, we will say, well, there's no answer because no number multiplied by itself, it could be negative. Well, now we're talking about a fifth root. So a number multiplied by itself 5 times, can that be negative? Well, because it multiplies itself an odd number of times, If the number was negative, it would stay negative. So here is going to be the fifth root of negative 32, which is negative 2. And then we want to square that. So our final answer is going to be 4. Okay, so just working off some more examples. Now we're dealing with a fraction. So this is going to be the same thing as the 6th root of 1 over 64 to the power of 5. So we could think of this as, again, this is sort of like the power to a power law. We could think of this as the 6th root of 1 over the 6th root of 64. But we're not actually going to do the 6th root of 1. We know that's always going to be 1. I just want to see that the power law still applies in this case, because really we can think of it as 1 over 64 to the power of 1 over 6. So what's 1 to the power of 1 over 6? Well, 1 to the power of anything is going to be 1. So this still applies. So the 6th root of 64 is 2. So I'm going to finish this over here. So it's going to be 1 over 2 to the power of 5, which is 1 over 32. So this example is just very similar to the one we just did in the warm-up. So 3 to the power of negative 2, that's going to be 1 over 3 squared, which is 9, minus 3 to the power of negative 1 is going to be 1/3. And then 9 to the power of negative 2 is going to be 1 over 9 squared, which is 1 over 81. So we have to convert to a common base of 81. So that's going to be 9 over 81. 3 goes into 81 27 times, so it's going to be minus 27 over 81, minus 1 over 81. So 9 minus 27 is a negative 18, minus 1 is going to be a negative 19 over 81. Okay, so that one sticks out a little bit because it's actually not dealing with rational exponents. So a couple more examples over here. So again, this one looks really weird because I got one square root and I get another square root. And notice that there's implied radix in each of these is a 2. So really, let's convert this. When we want to write as a positive exponent, we really want to convert a radicals into a rational exponent. So square root is going to have an exponent 1/2. And then we're going to do another square root in there. That's exponent 1/2 of 81 a to the 8th b to the power of 4. Okay, so we get 81 8 to the power of 8 to 8 b to the power of 4 times the power of half times to the power of half again to the power of a half. So this is going to be the same thing as 81 a to the 8th b to the 4th to the power of 1/4, because a half times a half is a quarter, and I sort of distribute or sort of take the power to a power law. So 81 to the power of 1/4, or the 4th root of 81. So what number multiplied by itself 4 times is going to be 81? That's going to be 3. And 8 times 1/4 is going to be 2. And 4 times 1/4 is just going to be 1. So there's the final answer, just 3a squared times b. So here's an example where we're not dealing with a radical, but we're just dealing with a rational exponent, and we're just going to do the power to power law. So here we're just going to say 64 to the power of 2/3 times x. Well, 6 times 2/3, the 6 reduces with 3 to 2, so that's going to be x to the power of 4. And then y, negative 9, cancels out the 3 to give us a negative 3 times 2 is going to be y to the power of negative 6. So again, we only want positive exponents. So in this case, y is going to become the denominator with the power of 6. X stays on top with the power of 4. And the 64 to the power of 2/3. Well, I'm just going to do this off to the side. So this is going to be the cube root of 64 squared. Well, the cube root of 64 is 4. So this is 4 squared, which is 16. So we're left with 16 on top over here. Okay, and this next question looks really tricky. So one of the things is going to just rewrite everything as a rational exponent. So understanding the square root really is exponent 1/2. So all of this to the power of a half. Well, x squared to the cube root of x squared is going to be x to the power of 2/3 times x, so x to the power of 3, but we want the fourth root of that, so it's going to be x to the power of 3 over 4. So here, I think I'm just going to take care of what's inside the brackets and just deal with x to the power 2/3 times x to the power 3/4. So again, this is the product law. I'm going to add the exponents together. So 2/3 and 3/4 is common denominator 12. So that's going to be 8 over 12 times x to the power of 9 over 12, all to the power of a half. So this is going to be 8 plus 9 is 17. So this is x to 17 over 12. Let me write that a little better. 8 to the power of 17 over 12, all to the power of a half. Well, 17 over 2 times a half is just going to be 17 over 24. So that's our final answer there. I think this is the last example. Simplify as a single radical. So here we're going the other way around. So really what we want to do is sort of convert all the radicals into rational exponents so that we can simplify everything. And once we got everything simplified to a single rational exponent, then we convert that to a radical. So let's take the fifth root of x to the power of 8. Well, that's going to be x to the power of 8 over 5 divided by, well, the square root of x cubed. That's going to be x times 3 over 2 all cubed. And the next thing I would do, while just recognizing the 3 doesn't cancel anything in my fractions, I'm just going to take care of inside the brackets. So really using my quotient rule, this is going to be x 8/5, 8 to the power of x 8/5 minus 3 over 2, all to the power of 3. So I just go off to the side. 5 and 2 is a common denominator of 10. So it's going to be 16 over 10 minus 15 over 10. Oh, that works out nicely, which is just 1/10. So here you get x to the power of 1/10, all to the power of 3. So this is the same thing as, well, I could almost convert this to a radical right away. But I'm just going to go back to what I just said, have it as one simple, has one rational exponent. So there's going to be x to the power of 3 over 10. And how do I rewrite that as a radical? Well, again, my base, so my radicand is the base. The denominator is my radix, so that's 10. And then this is all to the power of 3. Okay, so that's how we can answer that question as simplifying to a single radical. All right, so you don't have to do the homework, but instead you have a whole bunch of worksheets that you sort of practice on. For extra practice, you are more than welcome to do these extra questions from the textbook as well.